Okay, today we are going to talk about work, power, and energy. Work in physics is a little bit different than work in life. Hopefully, right now you are all doing your work of watching this video and taking notes for the lesson. But if we consider you a large object located with your center of mass, you're not actually moving. Your finger might be, etc., but we'll consider you on a large scale. According to physics, you have no work is force times distance. You're not moving, so you are doing no net work. Okay. For the sake of this definition, I'm glad you guys are all working. Okay. Not work in physics does not necessarily mean the same thing as work in life. So work is force times distance. Now, there's an implication here that the force is pushing or pulling in the direction of motion. Um, but if I've got something moving along a flat surface like this, let's say it's a little car, and you're pushing it at a downward angle, some of your force is not effective for work. So you'll see this other definition for work. Work equals force times distance times cosine theta. And what that is doing is effectively going, this component here, x, of the force would be equal to F cosine theta. So it's saying the force in the direction of the motion. So you could also think of this as Fx d. Okay, so it's that component that is in the same direction that the work or that the object is moving. Remember, if an object is not moving, doesn't matter how much force I put on the wall trying to push it. If the wall doesn't move, I've done no work. Okay. So work becomes a very useful thing. Work is also equal to the change in energy. So if the energy of something is changed, work was done. If work was done, the energy of that object was in some way changed. Okay? But right now, I am teaching a lesson. I'll walk around some today. What is going to do more work today, me or my car? Well, my car is capable of doing a lot more work than me. It can exert much greater amounts of force, um, but it is not capable of exerting them as quick. But it's currently not exerting any force because it's sitting in my driveway. Okay, so we also need this measurement that we'll call power. And power is the amount of work that can be done in a time interval. So my car can exert much more force to much greater amounts of work every second than I can, even though some days it doesn't do very much work at all because it just sits around and I do a lot of work. Okay, so we have this power. Power is equal to work divided by time, or you can think, remember, work is force times distance divided by time. So power, again, force divided by time. Essentially, how much, or work divided by time. How much work can I do in a given amount of time? Usually that amount of time is per second. The common unit of power is the watt, and watts are equal to a joule of energy. Joules are the unit for energy or work. A joule, watts are a joule per second. You'll often hear things in kilowatts. That's just 1,000 watts, megawatts. Um, those are a million watts. So just using general metric prefixes. The other common unit for power is the horsepower. And yes, this is kind of a random one. And the definition of how they came up with it is also even more random. But the idea is that it is how much power can a horse generate, which is, depends on the horse very much so. Okay, so that is power. Now let's talk about forms of energy. And form number one of energy is potential energy. We're going to talk about mechanical energy, and mechanical energy, you'll see this was on your pretest. Mechanical energy is kinetic energy and potential energy added together. So potential energy is energy that could be released based on something's position. And you can take a look at this position here. We've got this hanging block. If I cut the cord, it will fall, having energy. It had that energy based on its position. So the two types of potential energy, we're mostly going to focus on gravitational, but gravitational potential energy is simply mass times the gravitational acceleration, 9.81, times height. You could also think of it as force gravity or weight times height. Okay, either one of those is the same. So potential energy is all based on position. Now, height we usually think of as height above the ground or potentially height above the lowest position it can go. With like a swinging pendulum, we'll often put the height as height above the bottom location. Um, so currently I'm sitting on the first floor of my house. I would say I'm at a height of, well, let's just say my feet. My feet are on the ground, so my height's 0. Now, if my floor breaks, I'm going to fall through into the basement, and my height's going to be -8 feet or something like that. When we use this, we always talk about a change in energy. And so whether I go from 0 to -8 or 8 to 0, it ends up being the same change. So you can pick your height as anything as long as you keep it consistent for the entirety of the problem you're solving. Okay. Usually you just pick the height as the ground. It's the easiest. Okay. That would be the most sensible. If you pick it as something else, please be specific that you did. The other type of potential energy we're going to talk about is spring or elastic. Elastic and spring kind of work the same. A spring, you're familiar, I'm sure, with the coils. You can either press them in or some of them you stretch out. And the spring potential energy is 1/2. K stands for the spring constant, which is basically how hard is it to stretch or compress this spring, times the distance it's compressed or stretched. So if I've got a spring here, and this is its default length, and I stretch it out, this change in length between my regular spring, unstretched spring, and my stretched spring is X. Okay? So that is spring potential energy. Those are both types of mechanical energy. Mechanical energy is energy of moving things, or in this case, potential. We'll deal with all kinds of energy in the future, but for this unit that we're doing on mechanics, we're going to focus on mechanical energy. The other type of mechanical energy is kinetic energy, which has an equation of 1/2 mass times velocity squared. And kinetic energy is energy of motion. Okay? Motion energy. So how much is it moving? The energy of motion is based on the mass. That's why there's the mass in the equation. But it's more importantly based on the velocity squared. Velocity, because velocity is squared. It's essentially twice in the equation. Or sometimes they'll say it as speed, because when I square any number, it becomes a positive, which speed is just always the positive. It's velocity without the direction. So the kinetic energy does not depend at all on which way it is moving. Important thing to note with potential energy. Okay, we've got all three of these balls made it to the top in a different way. One here went straight up, one goes up a ramp, one is moved upstairs. They all have the same height. They all have the same potential energy, which means it was the same, because remember I said before that work is equal to change in energy. It was the same amount of work to raise them up to this top here, regardless of how I got it there. Okay? So we can do a quick little check here. How much work is done lifting a 100 Newton block of ice a vertical distance of 2 meters? Well, it's 100 newtons. It gave me the force gravity. Work is equal to force times distance. That's 100 times 2, or 200 joules. Now it says how much work is done pushing the same block of ice up a 4-meter long ramp. My force is in the direction of motion, so it's 50 newtons times 4, again, 200 joules. I think they're assuming they end up the same height. We're also assuming here that the ice has no friction. Okay, what is the increase in the block's potential energy in both cases? Well, 200 joules of work was done, so it has increased 200 joules of energy. Okay, that is potential energy is all about position. Kinetic energy, all about speed. Okay. So work can equal a change in kinetic energy. Can be net force times distance. But the key thing here with kinetic energy is that it is about energy of motion. The more mass you have, the more energy you have of motion, but also the more speed you have. Okay, those are very important. And it's going to lead us into this idea of conservation of energy. And you're going to do the energy skate park, which is going to lead you to conservation of energy. It should be a pretty easy example, but we can look at a quick example here. We've got something, a circus diver on the top of a pole has 10,000 joules of potential energy. As he comes off, when he gets to halfway, he's got half his potential energy. At 3/4 of the way, he's got 3/4 at 7,500. Notice when he gets to the ground, he's got 0. Um, Notice that his total energy is always the same. It's always adding to 10,000. Okay, so any potential energy that he loses gets converted to kinetic energy as he picks up speed. Yes, we are ignoring air resistance and any kind of friction in this. Okay, in what's called a conservative system, we do not worry about air resistance or friction. We simply say energy is conserved, and in most cases, it's approximately true and gives us pretty good approximates. Okay. Yes, energy with friction gets converted to what's called thermal energy, as when you rub your hands together, it produces heat. Friction produces heat. So yes, some is lost to that, but generally not much. And we can treat a lot of situations if we're willing to approximate that there is no friction and air resistance. We can just think about the conversions of energy and figure out how fast things are going, etc. Okay. Back to the work kinetic energy theorem. The work kinetic energy theorem, I've been saying this one, that work equals change in energy. Well, that's called the work energy theorem. Sometimes it's called the work kinetic energy theorem because work equals change in kinetic energy. But work can also equal a change in potential energy. Okay. So the work done, when we think of work, we always think of work done on an object, not work done by an object. So as a chair is pushed across the room, we don't think of you pushing the chair across the room. We think of the work done on the chair as it's pushed across the room, the force on the chair. It's a little different way of thinking about it in terms of physics. Okay, we'll be doing more things with these equations tomorrow. Um, One thing that's very important is simple machines. Okay, machines are a way of reducing the force, but they do not reduce the work. Okay, so here we've got an example of the lever. The lever and fulcrum here. Okay, we know probably from using a seesaw, you've probably done this before at once in your life, that if you're heavier, you need to move towards the middle and have less distance. Well, what happens is, as you get more length, this is called leverage, you've probably heard of that, you require less force, but then you get less distance. So this machine doesn't change the amount of work. The work is still equal in both cases. However, now I can actually exert the force. The advantage of the machine is it reduces the force to something that maybe I can actually exert. Now I'm going to have to increase the distance to do that. Another simple machine, it's actually a lever, is my elbow. My bicep attaches right here. It's kind of like a reverse lever. I have a lot of force here, but I get more distance in my arm. So you actually can have levers. You can have a lever with the fulcrum here and the useful force there and the applied force here. So maybe you're lifting something. Anybody ever shoved a board under something and lifted it up using the length of the board? Okay, that becomes a very actually useful thing. That's what your elbow is doing. You're actually getting more length out of it. You're actually applying the force here on the inside, and you get increased distance with but less force. So your muscle applies actually more force to get extra distance. So machines can actually work both ways. Oftentimes we use them to reduce force, will increase the distance, but it can work the other way. Okay, that's one simple type of machine. Another simple type of machine is the screw or a jack. Often a simple jack pretty much uses a screw to lift things up. You twist and you get a little bit of gain with the screw. As it's twisting, you're moving a lot more to get that. A lot of times with one of these jacks, you'll have a big arm here sticking out, and it moves just a little bit for a full rotation. Another type of simple machine is the ramp. Okay. So our simple machines here, the lever, the screw, The ramp, what does a ramp do? It allows us to really all we're interested in is about gaining this height. We're using additional distance to do it so we don't have to go straight up. And this comes into play all the time when you're trying to get something heavy into the back of a truck. You can't just pick it straight up and put it in, but you could roll it up a ramp using lower amounts of force for a greater distance. The last one we're going to talk about is the pulley or the pulley system. A single pulley can often just be used to, all this pulley right here is doing is switching the direction of the force. This thing is being supported by one object. This one, however, has a force tension up on both of these ropes. Both of those ropes are holding it up. So the person is only having to exert half the force. Now, as they pull up the rope, they pull essentially half from each side. So they only get half as much distance of lift as they pulled in rope. You can often get complex pulley systems with multiple pulleys, and the more strands of force you have here, or strands of rope, essentially, the more you can reduce the force. Now, again, if you reduce force, you must add extra distance because you cannot reduce the work. Okay. And these are all nice ideal machines. Ideal machines have no friction. They have no additional force. So my simple machines, yes, a pulley does have actual friction. So there is generally you need to exert a little bit more force than you get out, which means you're essentially doing more work than what you get out. Okay. All machines have a little bit of friction, which means I'm having to exert a little bit more force than my ideal force, compensate for that friction as I slide something up the ramp. Maybe I'm rolling it up on wheels. Okay. So efficiency here is useful work divided by total energy input. So efficiency essentially is just the ratio of the energy that I actually could use out of it. So a perfectly efficient machine, this efficiency is 100% or 1. I can never be more than 100%. I can never get more energy output than I got input. That violates some of the laws of energy. Lots of things, though, are not nearly 100%. For instance, cars, a really efficient car is like 40%. Okay. You only actually get 40% of the usefulness out of the fuel. Okay. You burn all this fuel, it's got a lot of energy in it, but only about maybe 40% at best gets converted. A lot of pulley systems have some friction in them. Usually you can get more than 40% efficiency, but maybe not always. Okay? So that's kind of a quick summary of chapter 7 of work, energy, machines, and efficiency.